Good afternoon. Just looking at picking up where we left off, okay, in the case of where we cross over from various types of one-to-one functions and where we had the examination of the various layouts where we have one-to-one functions and their corresponding inverses. And we had most recently with exponential functions as a one-to-one function where the inverses we have to be logarithms. And we looked at a few properties of logarithms, and again, for the first property, okay, we have just kind of like reminiscent of what we have had with taking the inverse of a one-to-one exponential function, where we were looking at solving for y, where we had come down to the base a logarithm of a to the y is equal to y. Well, we have in terms of the variable x, again, we had the base a logarithm of a to the x is equal to x. And again, akin to this property, okay, and we will be seeing this sort of toward the end of what we have in the section involving exponential and logarithmic equations. We have a to the base a logarithm of x is equal to x. And also for what we have in terms of computational purposes, again, for generic scientific calculator, okay, that is going to pretty much come equipped with natural and base 10 logarithms, but for logarithms of other bases, you will not typically see those. And this is where we had the change of base formula, where we had the base a logarithm of m, you can say is equal to either the natural or base 10 logarithm of m with respect to the same logarithmic base of a. And for what we have in the case of the remaining property we looked at the other day, you had the base a logarithm of m to the r is equal to r times the base a logarithm of m. And for what we have in the case of the first and the fourth properties, we'll be involving those in the case of looking at what we will have in the case of interactions between distinct logarithmic terms. And for what we have in the case of the next item, okay, we're going to be looking at operations between logarithmic terms. And so for this part, okay, I'm just going to refer to this, okay, for what we have in the case of sums and differences of logarithms. And we'll kind of go in somewhat different directions, like engineering and reverse engineering. Like you will have one mode, we'll be looking at expanding a logarithmic term, and then you'll have going in the other direction where you're going to take logarithms in the same base and combining into a single logarithmic term. Okay, so for what we have regarding sums and differences of logarithms, and we have for the first, okay, see we have a base a logarithm, and we have of the product of m times n. Okay, so you have the attachment at m and n. Okay, and m and n, they're factors in the attachment and they are multiplying each other. And if I were to write in terms of adding or subtracting, now in the case of expanding the layout in terms of separating m apart from n, wherever you see multiplication, you're going to have the separation to where the translation will go from multiplication between factors to the addition of logarithmic terms in the same base, but where the attachments will be laid out and separated. Okay, so in this case, we have for the base a logarithm of m times n. So if I draw out separately, so multiplication is going to imply addition. And so as a standalone term, I'm going to have a base a logarithm of m. Then we'll have plus the base a logarithm of n. And in terms of combining logarithms, okay, it'll also work the other way. Base A logarithm of A plus the base A logarithm of n. And in case of combining logarithms, you're going to have addition to imply multiplication. Okay, so you're looking at the base A logarithm of m times n. And where we have, so this is the case of what we have with sums of logarithms. Now where the differences come from, say that in the case of expanding, okay, so we start out with a singular base A logarithmic term, and we'll have the operation of division. Okay, we have m divided by n. And for what we have in the expanded mode, okay, this will translate out to the base A logarithm of m minus the base A logarithm of n. Okay, and in the case of fractions, okay, whatever the attachment is in the numerator, the corresponding logarithmic term is going to be positive, and if the expression or factor is in the denominator, okay, as a standalone logarithmic term, okay, the denominator is going to be where, as a standalone attachment, this will be part of a negative logarithmic term. And again, in terms of contraction, I have the base A logarithm of m minus the base A logarithm of n, and this is going to be equal to the base A logarithm of m divided by n. Okay, and let's say that in the case of expanding, and let's say that if I express as sums or differences of logarithms, and we can say while converting exponents to coefficients. Okay, and so we'll just have as lead-off examples. And we'll say that we have here, okay, the base 3 logarithm of a times b. Okay, and again, if I have multiplication, I'm not limited to just two factors. It could be 3, it could be 10 for all I know. But for the base 3 logarithm of a times b, if I separate a apart from b, so you have multiplication is going to imply addition. So looking at separating, so we're going to have the base 3 logarithm of a plus the base 3 logarithm of b. All right. And let's say that if I expand the model, okay, ever so slightly, and we'll say that we have the base 3 logarithm, and we'll say this time around we have the letters u and v, and we'll say we have u to the second times v to the fourth. Okay, so you got the expressions in u and v multiplying each other and separating the variables. Again, we'll be using the operation of addition to undo the multiplication in the consolidated logarithmic term in the base 3. So you have the base 3 logarithm of u squared and we have plus the base 3 logarithm of v to the 4th. Okay, and now notice we have, unlike a and b, u and v are expressed, okay, to where we have them as bases that are to raised powers. Okay, so we're looking at converting exponents to coefficients, and this is going to go to where we have with the last property from the other day, if we had the base a logarithm of m to the r, where r is going to be written as a coefficient. Okay, and so we have in both of these terms, we got u to the second, so I can write 2 as a coefficient, and for the base 3 log of v to the 4th, I can write 4 as a coefficient. And so here we're going to have 2 times the base 3 logarithm of u, and we have plus 4 times the base 3 logarithm of v. Okay. And let's say that where we have another property to enter the scene. Okay, say we have the base 5 logarithm of 25 times x to the 9th. Okay, so if I look at separating, that is 25 from x to the 9th. Okay, so I have a base 5 logarithm of 25, and I have plus the base 5 logarithm of x to the 9th. Okay, now again, the 9 is going to become a coefficient. Now for the numerical attachment 25, okay, if you notice you have 5 for the logarithmic base 25, we have it as the attachment. And in terms of how 25 will interact with 5, well, we had it 25 is a multiple of 5, and it is also an integer power of 5. And so we're going to consider not only the 4th property from the other day, but also the first, where I can convert 25 in terms of the exponential base 5. Okay, so I can write the first term. So we have what's going to be the base 5 logarithm, and 25 is going to be 5 to the second. We have plus the base 5 logarithm of x to the 9th. And so for what we have in following through, okay, so the base 5 logarithm of 5 squared, again, the logarithmic base and the exponential base will cancel each other, so the log goes out altogether. So we're going to have just 2 left over. And for the second term, 9 is going to be brought to the front. So this will come down to 2 plus the base 5 logarithm, 9 times the base 5 logarithm of x. Now, looking at what we have, yes?
Can you show me again how those logarithms cancel out each other?
Okay, remember, if you've got, I'll give you a case. Now, again, we're going back to what we have with the base a logarithm of a to the x is equal to x. Now, I'll give you a case here. If I tried out, let's say, like the base 5 logarithm of 100. Okay, so just kind of give you kind of a case here in terms of how I was able to reduce. Now we got like 5 to the first is 5. 5 squared is equal to 25. And we've got 5 cubed is equal to 125. Okay. So for the base 5 logarithm of 100, because 100 is not an integer, it's a multiple of 5, but it's not an integer power of 5. Okay, so the base 5 logarithm of 100 in exact terms, that one cannot be reduced. And if I did like the change of base formula, okay, the base 5 logarithm of 100, okay, now you got 5 squared is 25, 5 cubed is 125, and 100 is a number that is between 25 and 125, so the reduction would be like somewhere between 2 and 3, but it would not be an exact number. But if I have like the base 5 logarithm of 125, okay, because we got 125 is going to be 5 to the third. And guess what? I have a perfect match, okay, because 125 is 5 to the third, base 5 logarithm of 5 to the third. The 5's will cancel out, and that is going to go to 3. All right. Now let's say that if we have a case where we have division involved. Here's another item, okay, where we have reduction. Okay, say if we have 4 all over b to the third. Okay. All right, so we got the operation of division between 4 and b cubed. So in this case, right, we're going to have division is going to imply subtraction. So here we're going to have the base 2 logarithm of 4 minus the base 2 logarithm of b to the third. Okay. Now, if you notice, okay, we have 4 and 2. Now 4 is a multiple of 2, and it is also an integer power of 2. So the base 2 logarithm of 2 to the second. And have minus, okay, the base 2 logarithm of b to the third. Okay, and again, you have a match between the logarithmic and exponential basis, and that's going to reduce to the exponent, okay, 2. So that's going to be brought again out. So we got 2, and again for minus the base 2 logarithm of b to the third. So that 3 is going to be converted to a coefficient, and so we have for this end result, okay, we'll have after the 2 we'll have minus 3 times the base 2 logarithm of b. All right, now let's say if I have simultaneous appearance of both multiplication and division. Now let's say that if I have a base 4 logarithm I'll say that I have for the factors. Okay, so I'm going to say that I have 15 a to the third, b to the second, and we can say we have all over 64 times d to the fifth. Okay, all right, so I got 3 factors in the numerator, 2 in the denominator, and okay, so we got multiplication and division going on simultaneously, and in the expansion I'll be looking at both addition and subtraction, and you can put the terms in most any order, but usually what I like to do is just take care of what is at the top first, and at the top, okay, the attachments will be affixed to what will be positive logarithmic terms. Okay, so you have like 15 is at the top. So we're going to have a base 4 logarithm of 15. And then we have a cubed is at the top. So we have plus the base 4 logarithm of a to the third. And for b squared, that is also at the top. So we have plus the base 4 logarithm of b squared. Okay, but now we're 64 and d to the 5th on the bottom. Okay, those respective logarithmic terms are going to be subtracted. So we have minus the base 4 logarithm of 64. Then we have minus the base 4 logarithm of d to the 5th. Okay, now for the first term, we had the base 4 logarithm of 15. Okay, 15 is not a multiple of 4, and it's not even an integer power of 4. Okay, because like 4 to the first is 4, 4 squared is 16, and since 15 is surpassed, okay, that ship has already sailed. Okay, so we're still going to be stuck with the base 4 logarithm of 15. And we have with the next term. Okay, so we got with the base 4 logarithm of a to the third. Okay, so you can write this expression with 3 at the front. And for the base 4 logarithm of b squared, I can put the 2 at the front. So 3 times the base 4 logarithm of a. I have plus 2 times, okay, the base 4 logarithm of b. Okay, now I'm just going to bring this on down just a little. Okay, now for the base 4 logarithm of 64, now this term, this expression can be reduced. Okay, now 64 is a multiple of 4, and it is also an integer power of 4. Okay, remember, like 4 to the first is 4, 4 squared is 16, and 4 to the third is going to be 64. So rewriting 64 in terms of the exponential base 4, that's going to be 4 to the third power, and that is equal to 3. So we have for the term that follows, okay, that's going to be the subtraction of 3. And we have with the remaining term, we have d to the 5th, and 5 is going to be placed at the front. So we'll have minus 5 times the base 4 logarithm of d. Yes.
So even though denominator is multiplied, you're still going to subtract.
You're still going to subtract.
Why?
Yeah, I'll show you why. Because there's another way that you could do this, but think of it like this. In fact, I'll give you, let me throw in this extra example. Even though it is multiplying, here's the way you can go about this. Okay, so if I have like base 2 logarithm, and we'll say we have a all over b times c. Okay, so you will have the base 2 logarithm of a. And say you have minus the base 2 logarithm of b times c. But guess what? So I had the base 2 logarithm of a. Now b and c are multiplying each other, but if I expanded out the base 2 logarithm of b times c, It's like, now if I had just the base 2 logarithm of b times c, that's a base 2 logarithm of b plus a base 2 logarithm of c. And because that term or that attachment is in the denominator, you're still going to be distributing subtraction. And guess what? It still comes out to the base 2 logarithm of a minus the base 2 logarithm of b. And guess what? I still have the negative of the base 2 logarithm of c. So for any attachments that will be at the top, they'll correspond to positive logarithmic terms in the base. Any attachment that is at the bottom ultimately is going to be, once you have the factors as standalone attachments, it'll be part of negative logarithmic terms. And this is like such a case here. And let's say that, looking at what we have for determining the following. And I'll tell you what, just to kind of kick things off, okay, just for the next few moments. Okay, let's say that if we're looking at, let's see. Okay, just 3 items we can look into. Let's say if we have the base 2 logarithm, and see we're going to have b to the third, c to the second, and d to the fourth. Let's say we have next, okay, we'll say we have the base 3 logarithm. Let's say we have a to the third, and we have a b times b raised to the x plus 1 and we'll say that with the third item. Let's see what we get for the base 4 logarithm. And say we have a 19 a to the third, c to the fourth, now say we have all over 16 times b, where b we'll say is raised to the y minus 5 degree. Okay, so for the next few moments, let's see what we get for our individual logarithmic terms. First one we have in base 2, second we have in base 3, and third case we have in base 4. So let's see what expanded terms we get among these results. Okay, for our logarithmic terms. Okay, so we have for the first item, okay, we're looking at the base 2 logarithm, b cubed, c squared, and d to the fourth. And we have with the factors, okay, you have multiplication in terms of the interaction that is going on. And looking at expanding, so again, we're going to have multiplication is going to imply addition. So adding what we have for b to the third, c to the second, and d to the fourth. All right, so we're going to initiate, okay, so we have base 2 logarithm, b to the third, and we have plus the base 2 logarithm of c to the second, and we have plus the base 2 logarithm of d to the fourth. Okay, and we have with the letters b, c, and d. Okay, those are bases to which we have raised exponents. And so for what we have in the set, okay, so the first term we're going to have 3 times, okay, the base 2 logarithm of b, And then we have plus 2 times base 2 logarithm of c. And then we'll have plus 4 times the base 2 logarithm of d. Now, for what we have in the second item, okay, is pretty much similar in nature, but this time we have b to a variable expression power, and we still have multiplication happening between a cubed and b, which is raised to the x plus 1 degree. And so just breaking up the multiplication and rewriting as the sum of base 3 logarithmic terms. So we have the base 3 logarithm of a to the third and we have plus the base 3 logarithm of b raised to the x plus 1 degree, and looking at rewriting the powers as coefficients. Alright, now for the first, okay, we have 3 times, okay, the base 3 logarithm of a, and then for the second term, now you have x plus 1 to go from power position to the coefficients, and what I need here is I'm going to have x plus 1 times, okay, the base 3 logarithm of b, and to denote, okay, now, so as a coefficient, now both x and 1 will be multiplying the base 3 logarithm of b. So what I'm going to need to enclose this to ensure that x is like 1 is multiplying the base 3 logarithm of b, I'm going to need parentheses, because if I don't have the parentheses, I'll have like x by itself and 1 times the base 3 logarithm of b, okay, apart, and when they need to be together. And it's kind of like the last example from the other day. So I had like the base 5 logarithm of t to the y plus 4. Again, when y plus 4 is converted to a binomial coefficient, you're going to have the translation where you have like the quantity of y plus 4 times the base 5 logarithm of t. And in this case, you would need parentheses. Now, for what we have in the case of the last of this trio, all right, so you have 3 terms in the numerator and 2 in the denominator. Okay, and looking at expanding, okay, so in the base 4 logarithm, okay, so I got 19 at the front, and if I work solely or at the front, okay, with just the terms or the factors in the numerator. Okay, so starting out with 19, then I have next, I have a to the third. I have plus the base 4 logarithm of c to the fourth. And then for what I have in the denominator, again, so terms or factors in the denominator, once you itemize, we have terms to be subtracted. You can just restate. Okay, so you have, okay, now 19, not a multiple of 4, nor is it an integer power of 4. So the base 4 logarithm of 19 remains fixed. For the base 4 logarithm of 16, again, 16 is a multiple of 4, and on the basis now, to be able to reduce even further, okay, now 16, not only must be a multiple of 4, but it also has to be an integer power of 4. So 16 is going to be 4 to the second. So the base 4 logarithm of 4 squared. Okay, so that is equal to 2. Okay, so for what we have in this regard, okay, so we have the base 4 logarithm of 19. Okay, we have next, okay, so 3 and the exponent out in front as a coefficient, so second term becomes 3 times the base 4 logarithm of a. And next, okay, so you have taking the 4 away where we have c to the 4th, okay, so we have 4 times the base 4 logarithm of c. Okay, next term we have the subtraction of 2. And again, shifting y minus 5 from the exponential position, okay, to coefficient. Okay, so got subtraction involved. Now we'll be looking at all of y minus 5. And it's going to be in parentheses, since that is going to be multiplying the base 4 logarithm of b. Okay, and so that will be your result. All right. Now, looking at what we have, let's say, with the properties. Yeah, so we've looked at the formulas through the lens of expanding single logarithmic terms into distinct terms in the same logarithmic base. Okay. Now let's say if we go in the other direction. Let's say that if we have looking at combining as a single logarithm, and let's say that we have, for starters, okay, let's say we have something like 2 times the base 5 logarithm of u minus 20 times the base 5 logarithm of v, and so we have minus the base 5 logarithm of z, and so we have plus the quantity. Okay, so we have x minus 4 times the base 5 logarithm of w. Okay, so we're going from expanding out to logarithmic terms to contracting as a single logarithmic term. Okay. All right, so all these terms are in logarithm base 5, and taking what we have now. All right, so part of the process. Okay, now when we had like our last step, we looked at converting powers as coefficients, and now we're going to take the reverse order. Okay, so if you see any coefficient other than 1 or negative 1, okay, you're just going to write as powers. So we have the coefficient 2, and this will become an exponent. Same thing with 20. That's going to become an exponent. So we have in the rewrite, okay, so we have the base 5 logarithm of u to the second minus what is going to be the base 5 logarithm of v to the 20th. And then we have minus the base 5 logarithm of z. and then you're going to have plus the base 5 logarithm. And this binomial will be converted to an exponent. We're probably going to have w raised to x minus 4 degree, and with x minus 4 as an exponent, parentheses is optional, but as a coefficient, the parentheses will be mandatory. Alright, so we have these terms, so we've gotten the coefficients, okay, outside the absolute value of 1 taken care of. Okay, so we have just the sums and differences of logarithmic terms. And once I consolidate as a single base 5 logarithmic term, in terms of where the attachments will go. Okay, so I have, first of all, I have a positive base 5 logarithmic term with u squared as the attachment. And since this first term is positive, u squared goes on the top. Next term we have with v to the 20th as the attachment. Okay, this is part of a negative base 5 logarithmic term, so the negative signals that v to the 20th goes on the bottom. Then we have next, we have another negative logarithmic term, so this will signal that z, just like v to the 20th, will go to the bottom. And then with the last term we had the operation of addition. So for the attachment we have in w to the x minus 4th, that is going to belong in the numerator. Okay, so you can write this as the base 5 logarithm of u squared times w raised to the x minus 4 all over v to the 20th times z. Okay. Now let's say that if we have, it's another item here, say we have 3 times the base 5 logarithm of 2, and have minus, okay, the base 5 logarithm of x. Okay, so I'm starting off with another set of base 5 logarithmic terms. Okay, and let's say we have with the third, we'll have plus the base 5 logarithm of z. And I have minus 17 times the base 5 logarithm of w. Okay, so you have a couple of constants, okay, to adjust and make into exponents. So 3 is going to become a power, and 17 likewise. Okay, so I had the base 5 logarithm of 2 to the third, and I'm sort of throwing this in like you have a run-in with Alex along these lines here. Okay, so right now we've got minus the base 5 logarithm of x. Again, we have plus the base 5 logarithm of z. And have minus the base 5 logarithm of w to the 17th. Okay, now if you were to consolidate, okay, like if this were a handwritten test and you wrote, you know, with the attachment at 2 to the third, I would count it correctly, but I think in the case of Alex, if you have this run in, you got the base 5 logarithm, and for 2 to the third, okay, we just go ahead and convert that to the constant. That's going to be the number 8. If you left it as 2 to the third, I would count it correctly, but I don't think Alex would. So go ahead and write it out. Okay, so just say the base 5 logarithm of 8. Again, we have the other terms before the consolidating. Okay, those will remain the same. So all the terms we have in a base 5 logarithm. And putting together okay, so you have first term, okay, have a positive base 5 logarithm of 8. Okay, since 8 originates from a positive base 5 logarithmic term, 8 will go on the top. Then we have x originates from a negative term, so x will go on the bottom. We have z attached to a positive base 5 logarithm, so z goes to the top. And last term, okay, we have a negative, and we have, with the attachment w to the 17th, we'll have in consolidating, w to the 17th will go on the bottom. Okay, so this will be one way upon which we can establish or present the end result. And tell you what, looking at combining as a single logarithmic term, and let's say we have 4 terms in the mix. Now let's see what we get as a single term, whereupon we have, let's say, 4 times the base 2 logarithm of x minus 2 times the base 2 logarithm. Let's say we have the quantity of y minus 3. Let's say we have plus 5 times the base 2 logarithm. Let's say we have of z squared plus 1. Let's say we have minus 2 times the base 2 logarithm of w. Okay. A little bit of a different layout, but all these terms are in the logarithmic base 2. And let's see what we get as a single base 2 logarithmic expression. Okay, looking at what we have upon looking at compiling as a single base 2 logarithmic term. Okay, so any coefficients outside of positive and negative 1, okay, we'll just go ahead and write as exponents. And so for what we have here, okay, so we got the base 2 logarithm of x to the 4th. Next we have the subtraction. We have that of the base 2 logarithm of y minus 3 raised to the 2nd. And we have plus the base 2 logarithm of z squared plus 1 raised to the 5th. And we have minus the base 2 logarithm of w to the 2nd. Right. And just converting the pluses and the minuses respectively into terms of multiplication and division. Okay, so we have for the first term, okay, so you have x to the 4th, and that's part of the first base 2 logarithmic term, which is positive, so x to the 4th, that will go to the top. Next term is a negative, okay, so y minus 3 squared will go to the bottom. Next we have z squared plus 1 to the 5th, that's part of a positive base 2 logarithmic term, so that part will go at the top. And last term we have the negative of the base 2 logarithm of w squared, and so w squared will go to the bottom. And so this will be the consolidated term that we have in this third case. Alright, now as a little bit of a segue to what we'll be looking at involving exponential and logarithmic equations. Okay. And again, just going back to our foundational one-to-one exponential function, there is an intermediate property we'll be looking at in terms of conversions and rewrites between exponential and logarithmic terms. And if we have, let's say, it's kind of going back. Okay, so again we had f of x is equal to a to the x. And again, a is a positive exponential term. Okay, positive, but with the exception of 1. And again, we had for f of x or y. Okay, again, that is positive. And we had crossover to establishing the inverse as a logarithmic function. Okay, there are a couple of items we have in the intermediate stages, okay, in between the first and the last layout. Again, just interchanging x and y. And there is a property that's going to involve this part of the process, x equal to a to the y. And again, freeing up y, we're taking the base a logarithm of both sides. Okay, whereupon we have what leads to y is equal to the base a logarithm of x. And again, so we have with the inverse at the base a logarithm of x. Again, the exponential base is still positive except for 1. And for the inverse, okay, what we had originally with y is greater than 0 for the one-to-one exponential function, we have required for x in the logarithm. Now for the interacting portions, okay, immediately after the interchange, I have x is equal to a to the y. And for the implicit layout for the inverse, we have y is equal to the base a logarithm of x. And we have tying together conceptually what we have with these statements. Okay, we have that y is equal to the base a logarithm of x if and only if x is equal to a to the y, with the constraints that a is greater than 0, with the exception of 1, and also again where x is going to remain positive. And looking at what we have and sort of consolidating what we have here between these statements. And I'm just going to kind of set up a table where we have like interchanges between exponents and logarithms. Okay, and if I were to express each item in terms of its exponential or logarithmic equivalent, okay, so you have concerning this statement. Okay, so y is equal to the base A logarithm of x. And we have that x is equal to a to the y. And we'll say we have, first of all, okay, say we have something in terms of y is equal to the base A log of x. Okay, so again, if I have like 3 is equal to the base 5 logarithm of 125. Okay, and let me mention, if I have like the logarithmic term on the left, constant on the right, I can just do the commutative property and just shuffle and place in the order of the constant on the left, logarithmic term on the right. So here you have x at 125, a is at 5, and y is at 3, and this will be carried over to what we have for the exponential counterpart. So, and the rewrite, x we have at 125, and we have is equal to a to the y, so a is at 5, and y is at 3. So the logical equivalent is going to be 125 is equal to 5 to the third. Now let's say if I start out with an exponential statement that we can agree on. Okay, say we have like 16 is equal to 4 raised to the second. So y is at 2, a is at 4, x is at 16, and rearranging in terms of the logarithmic equivalent. So again, we have y is at 2 is equal to the base A logarithm, and the a is going to be what was the exponential base, which we have at 4. So that 2 is equal to the base 4 logarithm of 16. And let's say that if we have that 2 is equal to the base 6 logarithm of 36. Right, so I have x, which is 36, is equal to a, which I have at 6, and to the y, which they're going to have at 2. So I have 36 is equal to 6 to the second. Now, and going back to calculator notations, say if I have a logarithmic statement that is going to be true, say if I have that 4 is equal to log of 10,000. Again, log, that's the implicit notation that the logarithmic base is going to be at 10. So with the exponential and base, which I'm going to get to, okay, if I take the logarithmic term and put it explicitly laying out just what the logarithmic base is, that's going to be at 10. So we can get the base 10 logarithm of 10,000. So we have x, and we have it 10,000. And a, okay, that is going to be at 10. And to the y, okay, which is going to be at 4. And say if I go out, okay, and say just another case here, if I have like 5 is equal to the natural logarithm of t. Again, log refers to a base 10 logarithm. ln is going to refer to a base e logarithm. And rewriting in terms of the exponential equivalent. So that which represents x is going to be at t. And a, okay, we'll have it e. So we have t is equal to e raised to the y, okay, which is going to be at 5. So have that t is equal to e to the 5th. And so you can have entities other than just single terms to represent x or y. And let's say that if I have like 2y plus 4 is equal to the base 5 logarithm of u. Okay, so I got 2y plus 4 is equal to the base 5 logarithm of u. So representing y in terms of the position, I had the binomial at 2y plus 4, Representing a, we have the number 5, and x is represented by the variable u. And just putting it in terms of the exponential layout. Okay, so for x, I'm going to have u is equal to a, which I'm going to have at 5. And I have 2 to the y power, which in this case is going to be all of the binomial 2y plus 4. And there's a couple more cases here. And let's say that if I have, let's say you have 1 over 32 is equal to 2 to the negative 5. So you have the reciprocal of 2 to the 5th. So you got x at 1 over 32, a at 2, and y at negative 5. And rewriting, okay, so for y, we have negative 5 is equal to the base a logarithm. So a is at 2. So negative 5 is equal to the base 2 logarithm, and we have of x, which is going to be 1 over 32. And if I have, let's say, another exponential statement, if I have that x is equal to e to the second. Okay. All right. So your y is going to be at 2. And for your base a logarithm, okay, we're working with a, which is going to be with the letter e. So 2 is equal to the base e logarithm of x, which you do have as x. So you have that 2 is equal to the base e logarithm of x. And you can also write that as 2 is equal to the natural logarithm of x. And just a couple of quick items here, crossing over to equations. If I have in the case of exponential equations with a common base, I'll show you just a layout on this one. Say if I'm looking at solving for x. Let's say if we have sort of an introductory case. If I have like 2 to the x is equal to 8, and I'm solving for x. Now if you notice, you have the bases at 2 and 8, and 8 is a multiple of 2 and is also an integer power of 2. So the 2 that is present, okay, that is already going to be the common base. So rewriting or writing or expressing both terms in terms of base 2. So we already have 2 raised to the x. Now for 8, that is going to be 2 raised to the third. And once I get to the stage of where I have single terms in the same exponential base, I can set the powers equal to each other. So right away I'm going to have that x is equal to 3. And I'm just going to cap this off, okay, with terms or numbers where the higher is going to be a multiple of the lower, but it is not going to be an integer power of the lower. And let's say that if we have 9 to the x is equal to 27. Now 27 is a multiple of 9, but it is not an integer power of 9. Think of it like this: 9 to the first is 9, 9 squared is 9 times 9, which is going to be 81. So for a common base, it'll be the number that will multiply itself to both 9 and 27, and that number is going to be 3. So if I convert both 9 and 27 in terms of base 3, so 9 is 3 squared, thus 9 to the x will be 3 squared to the x. 27 is going to be 3 to the third. And with the power property of exponents, now 3 squared to the x, that's going to be 3 raised to the 2 times x. So again, remove parentheses, exponents multiply each other. So you got 3 to the 2x is equal to 3 to the third. So I have single terms in the base 3, and this will be the green light to set the powers equal to each other. So we have that 2x is equal to 3, and we have with division by 2 and 3 halves. Okay, this will reduce to a decimal. That terminates, and so you can say that for the value of x, you can say x is equal to 3 halves. You put in fractional form, whereas the decimal, we can say we have 1.5.